Welcome to this tutorial that looks at application of the unit circle and the definition of sine, cosine, and tangent functions, trigonometric functions. So this is the fundamental basis of all of trigonometry. So it's a very important tutorial, and it's really vital that you understand almost everything that I present to you here, because in future, when we're coming back to these terms, I'm going to have to rely on your understanding. So, first of all, we have to, explain what is a unit circle. So, a unit circle is essentially, it's a circle, and it enables you to relate angles and coordinates together. Okay, so as you're moving around the unit circle, you're moving by a particular angle. Now, where you land, you may land on a particular spot on the circle. So let me just show you here. Let's say that we have moved from our positive x-axis. Now, this is our positive x-axis. And say we've moved by a certain degree. I don't know what that degree is. I'm not going to define it. But let's just say that we've moved from where we were at the x-axis. We've moved by a particular angle theta, and we've landed somewhere here. Now, all that we look at is the coordinate of where this particular line, where this line actually ends up being on the unit circle circumference. So that gives you a particular coordinate. You have a x value, and you also have a y value, because you've still got your y-axis and your x-axis present. And so what you can see is an angle can allow you to, use an angle to change the x and y coordinates. So if you make your angle really big, if you make it 120 degrees, you'll be all the way out here. Probably not that significantly, that might be 150, but you'll be all the way out there. So you'll get another type of x and y coordinate that's a bit different. So the angle and the coordinates are related together, and that's the basis of trigonometry, how to relate angles and coordinates to one another. Going back to the actual rules of the unit circle. So the radius of a unit circle is 1. Unit means 1. The radius, r equals to 1. We'll see where this is important a bit later. Angles are always measured from the positive x-axis. So I showed you a moment ago that I moved by a certain angle away from the positive x-axis. So that is generally the direction you move in. That would actually indicate, because I've moved anti-clockwise in this case, anti-clockwise is a positive angle in trigonometry, and clockwise would be a negative angle. Okay, so sometimes say that you've got negative 60 degrees, you move by 60 degrees here, and so you'll be, somewhere most likely over here on the circumference. So you've got another value, coordinate system. Okay, so negative angles are that way. This particular theta value, that could be potentially 20 degrees or 30 degrees or something like that. Okay, so a very important concept to understand. Now, so that's part of the rules. The rules state the angle is measured from the positive x-axis. The anti-clockwise angle is positive, and the clockwise angle is negative. And sometimes you might have cases of where you've moved more than 360 or more than 2 pi. And so this value should be subtracted. That's not a very clear sentence, but what it means is if you've moved around the unit circle by, say, you've moved by 600 degrees. 600 degrees, you've already moved more than one rotation around. So you've essentially gone the whole lap around and you're back where you started. And then you go around a little bit more until you reach the full 600. So sometimes to work out the angle, we want to just work out where we land, not necessarily how many laps around the circle we make. Okay, so theta in this case would be, say, 240. Okay, so 240 around that way means that you go around once and then you go around to 240, which will probably be somewhere there. So it's this whole section here that we're taking into account. That's going to be 240 degrees. So it is important to understand how to use unit circles. Now let's have a look at more closely the application of these. So I've already mentioned that basically we have particular values in trigonometry that you are relating your x and y coordinates together. So I'll just rub this out. So let's start from that again. Let's say we've moved a particular angle and this is the angle theta. And now, remember from the unit circle definition, we said that the radius is 1. So this distance here must be 1 unit. Okay, so all the way from the middle of the circle to the circumference is 1 unit. Now, we know that we've got some kind of... Can you see how we can set up a triangle? So we've got an x and a y coordinate. The y is going to be this size here. It's going to be y. And the x value is going to be right this part. Okay? So what we can do is we can actually use our fundamental trigonometric principles that we already are aware of from earlier year levels. So if we want to find what the value of y is here, we can see that that is opposite. And that side there is the hypotenuse. And then we can say sine theta equals to opposite over hypotenuse. Now, since the hypotenuse, this is a unit circle, what that allows us to do is this allows us to set up a very interesting relationship. The relationship is this one here. What it's saying is that if you have an angle and you take sine theta of that angle, you get the y coordinate. So rather than writing out this coordinate like so, we can also write sine theta instead of y. Because y and sine theta are equivalent. So that's the same thing. So you can see that y is equal to sine theta. Likewise, if I redraw this and I inspect the x value instead down here, so this is our y value and this is our x down here. Here we've got 1, we've got theta here. This is the adjacent. And that part there is the hypotenuse. So once again, we can just set up a relationship cos theta. So this is it. And so that we have to just type in cos theta. So a different way in trigonometry to write the x and the y coordinates is to write cos of theta and sine of theta. So let's say that we were somewhere, let's say that instead of making this theta, we made this 30 degrees, or say we made it 45 degrees. So say the theta value was 45 degrees. Automatically, you can find what your x and y values are by just replacing these angles here by 45 degrees with 45. So what that coordinate gives you is square root of 2 on 2 when you work it out, and also square root of 2 on 2 for sine of 45. So that's the actual coordinate of xy. So we used our angles, substituted them into our cos and sine value to obtain our coordinates. So once again, remember the whole basis of trigonometry is relating angles to eventually coordinates. So that's exactly what we did there. Now, what I have shown you here is I have shown you a special case of exact angles. Now, the reason why these are called exact angles, 45 is considered an exact angle in mathematics, and that's because it provides you with an exact coordinate. You can see that I actually didn't use my calculator for this question. I knew that at 45 degrees, cos is square root of 2 on 2. And at 45 degrees, sine is square root of 2 on 2 as well. So that's something that I already knew. Sometimes you may not know what they are. You may need to use your calculator. So at angles such as, say you had instead 35 degrees there. If we had 35 degrees there, then it wouldn't really be possible. You wouldn't have the same answers anymore. They are not exact angles. You would have to just work them out on the calculator. So when you work them out on the calculator, you may get a decimal place. But yes, this would be important to solve on your calculator. So not all values will have an exact coordinate. Okay, so let's have a look at some of the exact angles then. So this is where we're moving on to this table here. So the table states that you want to find sine of 30 degrees, sine at 30 degrees. So sine at 30 degrees, I'll just show you. I have a better unit circle up the top there, but I'm just going to use this very flimsy one. So we've got 30 degrees here. So we have 45 degrees here. And 60 degrees sort of going here. I'm going to draw the 60 degree one in. So that's 60 degrees. That's 45 degrees, and that angle there is 30 degrees. So now what we need to do is the values, the exact values are, there's only 3 of them, the exact coordinates that could be possible. There's a half, there's square root of 2 on 2, and there's square root of 3 on 2. These are the only ones I recommend remembering in methods. So half, so kind of the denominator in all 3 cases is divided by 2, whereas the numerator, the top part, goes 1, 2, 3. The smallest one is half, which is 0.5. So these are the actual values present. Now, if we look at sine of 30, we can see that sine of 30 is actually the smallest y value possible. Sine of 45 degrees, if we look at the y value, it's a bit bigger, and sine of 60 degrees is the biggest one. So as we go down, sine of 30 degrees is going to give us an exact value of half. Sine of 45 degrees gives us square root of 2 on 2. And sine of 60 degrees gives us square root of 3 on 2. Now note that you can also do this in radians, so this doesn't have to be in degrees. The radian equivalent is pi on 6, pi on 4, pi on 3. Okay, so then we look at the cos values instead. So we have 45 degrees and 60 degrees. Now, cos looks at the x value. So at 30 degrees, the x value is largest, then it goes smaller, and then it's actually the smallest at 60 degrees. So, unlike in sine, where the smallest value was 30, then it got slightly bigger at 45, and then it got bigger at 60. This is actually the opposite way around in cos. So when sine is smallest, cos is actually largest. Then here they are the same values, and then here we have a half. Now tan is actually looking at the gradient of these lines. Okay, so tan actually inspects what the value is of the gradient. Now, to work out the gradient of the function, we have to understand what tan actually is. So tan is equal to sine over cos. So this is a fundamental trigonometric property. Basically, tan is the gradient. The gradient is the change of y values, which looks at sine, over the change in x, which looks at cos. So to work out the at 30 degrees, to work out this table, so at 30 degrees, we have to substitute in tan of 30 degrees, which gives us sine of 30 degrees, all over cos of 30 degrees. Now, sine of 30 degrees is the same as a half over cos of 30 degrees, which is square root of 3 on 2. And then we can work out what that is. So half divided by, or times by, the reciprocal. Okay, and that cancels, and so we get 1 over square root of 3, which if you want, you can actually rationalize that denominator as well, so that becomes square root of 3 on 3. So that's what the tan value is. Now here, because you have the same sine value as you have cosine value, when you divide the two, you get the value 1. Finally, if you've got the theta being equal to 60 degrees instead, I'll just redo this calculation. So at 60 degrees, tan of 60 degrees equals to sine over cos. So we just take our sine value and divide it by our cos value, which is half. And then that becomes square root of 3 on 2 times by 2 over 1, which can then cancel and you get square root of 3. So that's what the value here is. So this is our exact angle table. It's going to be a really important table for you to understand and to use throughout these kind of trigonometric questions. So I really recommend that you have a very solid understanding of, what angles relate to what kind of coordinates. So you do need to memorize this table. However, we'll have a look at examples. So let's have a look at how we complete these examples. So solve the following. So with these kinds of questions, what you're doing is you are told where the angle is. So you're told that you have to move to 120 degrees around the unit circle. So here is a unit circle. And it's always quite nice to have a drawing shown, but so we start from here, and we're actually moving all the way around by 120 degrees. So I straight away want to show that that's 120 degrees. Okay, so what we have here is we need to obtain the equivalent value of sine of 120 degrees. Now, sine of 120 degrees, if you can see here, it's going to be, sine is the y value, so it's going to be this little section up here. Okay? So that's the y value. Now, I've made that really small to see. So we have, at that point there, on the circumference, we have an x value and a y value. We're only interested in our y value. What I'm going to do is, just because I was such a terrible drawing, I'm going to make it a little bit bigger and hope that I'm not making it small again. 120 degrees. Actually, that angle inside there, that's not going to be 120 degrees. That's actually going to be 180. 180 take away 120. So that's going to be 60 degrees. Now we're interested in finding the y value, which is this value here. So you can use your trigonometry. You know that to find that point there, that you can just go y is equal to sine of 60 degrees. Okay, and then using your exact table from just when we looked above there, we know that sine of 60 degrees is square root of 3 on 2. Okay, so the whole answer of sine 120 degrees is square root of 3 over 2. That's the exact value. Now, notice how in quadrant 1 and in quadrant 2, the value of all y values are positive, right? Because remember that this is the positive y quadrant. Down here, you get negative y values, right? Just from coordinate your axes and knowing that up is positive y, down is negative y, across is positive x, and on the other side is negative x. Now, so every answer of sine that falls in quadrant 1 and 2 is going to be positive always. And every single time a solution falls into quadrant 3 and 4, sine is going to be negative. Cos might change. So in quadrant 1 and 4, cos is actually positive because that's where positive x values exist. And in 2 and 3, cos is actually negative. So that's just a very important kind of concept to remember as you go through these problems. Okay, so let's have a look at the next question. So the next question is, I'm just going to make some space. The next question looks at sine of minus 25 pi over 3. I'll try to make this a bit bigger. So, 25 over 3, and you're going negative, so you're going that way. Not 250. 25 pi over 3. Okay, so we know that probably this particular the closest number that is exactly divisible in 25 over 3 is 24. So if we just change this into a mixed fraction, so this is -8. We don't need the negative ones. We know what direction this is going in. So so it's 8, and you have pi on 3 left. So 1 pi on 3. Okay, and then we end up going, finally, in the end, we end up going by, because this is still minus, we end up going to square root to pi on 3, which is that angle there. So pi on 3 is going to be where we land, and this is going to be the fourth quadrant. Okay, so we are going to be in that particular location. So if I again make this slightly bigger, and remember, you won't always have to think of it in this kind of way. You may be able to see it straight away. If I was interested in getting that y value there, because this is my coordinate where there's x, this coordinate here is the one I'm looking for, x and y. I'm particularly interested in the y value though, so I'm just going to be focusing on y. So I already know that the radius here is 1, and so what's important to do is we're going to have to just figure out opposite, and so we're finding sine of pi on 3 equals to y. And that shouldn't be a surprise, because we have been through the question of where, you know, whatever angle you get, you just substitute it into the sine function. The sign outside of this function should be a minus, because that's going to be, well, it is in the fourth quadrant. In quadrant number 4, you can see that all the y values down there are negative, okay? So in that, all these values along here, along this axis, are negative. And so what we end up getting is negative, let's have a look. Pi on 3 is the equivalent of 60 degrees. So sine of 60 degrees is square root of 3 on 2. So the entire answer is negative square root of 3 over 2. It's going through, now we're trying to find a cos function. So we're trying to look at x values. Once again, we draw a basic unit circle. This is negative x, and this is negative y. Okay, so we're going in the negative field again. We're going by 13 pi on 4. Now 13 pi on 4 is a little bit greater again than, it actually becomes 3 and 1 over 4 pi, which is the same as saying 3 and pi on 4. So what's happening is you're going by 3. You're doing 3 rotations of pi, and then you're going by a quarter pi. So, so 1, 2, 3, and then an extra quarter. So you're ending up there. Okay, so ending up, that's pi on 4. Okay, now I'm going to have to get some more space done here. Too many questions to deal with all at once. Okay, so that angle there is pi on 4. So we know that we can rewrite this as cos of pi on 4 straight away, but we need to put a negative in front. And the negative needs to be placed in front, because we can see that that distance here along the x-axis is actually negative. Okay, it's negative x values. So the coordinates of x is negative square root of 2 on 2 and some kind of y value. Okay, but we're not interested in the y value, we're only interested in the x value, so that's negative square root of 2 on 2. Okay. Let's have a look at tan now. So tan of 20 pi over 6. Okay, so tan of 20 pi over 6. Now, once again, we can break this down into tan of 3. 3 times 6 is 18, and then we have 2 over 6 left, and we have a pi on the outside. So sometimes it helps to break things down like so. So we've got tan of, so we're going by around the unit circle. We're starting, it's now going in the positive field. We're going by 3 pi. So 1 pi, 2 pi, 3 pi, 3 1/3. The computer's doing something strange. Okay, so this angle here is pi on 3. Now, tan is a little bit different. If you consider what tan is saying, in this case, tan is the gradient. So the gradient here and the gradient in the first quadrant, that's all positive gradient, isn't it? So it's a positive line. Having a gradient in this quadrant, quadrant 2, and then quadrant 4, would actually give you a negative gradient. So what we can do is we can just say, okay, well, tan of 3 1/3 pi is equivalent to, we have to look at our exact table, exact value. So tan of pi on 3 is 1/3. Sorry, not 1/3. It's square root of 3. Okay, so the entire answer, that's just going to be square root of 3. So essentially, all you're doing is you're identifying where you are and then whether the answer is positive or negative. So, in this question here, you've got negative 23 pi. So negative 23 pi, you're going around that way. And so you're going 1 pi, then followed by 2 pi, then followed by 3 pi, then 4 pi. So you see that soon that this gives you even values of pi, and this gives you odd values of pi. So in such a case, you've got sine of minus 23 pi can just as well be written as sine of pi, because that's where you end up at the odd side. And sine of pi is just equal to 0, because the y value at that, there's only an x value of 1, because you're on the axis, so there's an x value of actually minus 1, and there's a y value of 0. Okay, so let's have a look at the next question, question F. So, sine of 45 pi on 2. Okay, so sine of 45 pi on 2. Now this can be summarized, this can be simplified. 45 over 2 is the equivalent of saying 22.5 pi. And 22.5 pi means that you're going around the circle 22 times, so you end up there, and then you're moving by half a pi, which is right here. So you go 22 pi, and you go around 22 times, and then you go that extra half a pi. So the coordinate at that location, the coordinate for the x coordinate is 0, and the y coordinate is 1. Because we know that from there, if you just go vertically up, the radius is 1. Okay? So therefore, you could just say that the entire thing is 1. So that's the y value. sine always looks at the y value of the coordinate. Okay, so let's have a look at this next few questions. Maybe we can squeeze them in here. Okay, so tan of negative 41 degree is negative 41 pi. Once again, if I draw a unit circle, if I go around this unit circle by pi, this is an odd number of pi on this side, and this will give you an even number of pi's. So in the case of tan of negative 41 pi, that's actually going to end up being the same as just saying tan of pi, 1 pi, which is the very basic odd number of pi's. And in that case, if you think about what that means, remember that tan means the gradient. So if you think about the gradient when you're horizontal or flat, the gradient is actually going to be 0. Okay, whereas this one, is tan of 11 pi on 2 is the same as saying 5.5. Now 5.5 pi is going to be, well, you're going to end up going to the odd number of pi's and then an extra half a pi. So the gradient of that red line there, the gradient is undefined. And it's undefined because it's infinitely just got rise and it has no run. So it's not defined. Okay? So tan, usually when it lands on the axis, it can either have two values. It can either be undefined or it can be 0. Now, here where we see cos of 0 degrees, okay, can't find the pen, okay, found it. Cos of 0 degrees, once again, we'll draw out a unit circle. Cos of 0 degrees means you have not moved from the x-axis at all. You're still on it. And so the coordinate here is 1 and 0 because there's an x value but there's no y value. And remember that cos looks at the x value, so that's just going to be 1. So that was equal to undefined. Remember to actually answer the question equals to 0, etc. So using the unit circle is very important. It's important to draw out the scenario that you have and to try to visualize it using the actual unit circle. It does take a little bit longer, but it's worth the visual to make sure that you're actually getting the question right.